All right. I hope you guys are doing well. Today, we will continue talking about clustering. We're going to do k-means clustering, but we're going to complicate things a little bit by adding a kernel function, okay? So I guess just before we get into it, we'll just review k-means clustering. And the algorithm there is you're trying to determine how many first you determine how many clusters you're going to search for. And then your first thing that you're going to do is you're going to randomly assign points in your data to each of the clusters. And then once you do that, you calculate the centroids. And then you reassign values to clusters by associating the values to the data to the cluster with the nearest centroid. And then you just kind of go back and forth between recalculating the centroids and reassigning points to each cluster. All right, and so here's just an example. I've got some dots here, and we just randomly assign them to either black, red, or green. And then we go through and we find the centroids of each one, black, red, or green. And when we do that, almost everything's split between black and red, and only a few points get associated with green. So when we do that, we recalculate the centroids and we get this. Then we recalculate assignments, and these ones get associated with green. These ones still remain black and red. And when we recalculate the centroids, we redo the assignments, we recalculate the centroids, we redo the assignments, we recalculate the centroids, we redo the assignments, we recalculate the centroids, and this time when we redo the assignments, there's been no change, so this is when we say it has converged. Okay, so it's kind of neat to see, right? So random, centroids, reassign, centroids, reassign, centroids, reassign, centroids, reassign. Recalculate the centroids, redo the assignments, and then nothing changes. Okay, so that's how we know our data has converged. Okay, and so this would be the result of k-means clustering for this data set. Okay, so what we will do is we will do k-means clustering with kernels, okay? So if you recall, a kernel function, what it does is it applies some kind of transformation function, okay, to your vector x, and then it takes the inner product of the resulting vectors, okay? And so if you have what we call a linear kernel, then the transformation function is just the identity, and thus the inner product of this is just going to be, you know, xa transpose xb, or it's basically the equivalent of the dot product, okay? That's what we have here, okay? But there's other kernels and other transformation functions in other kernels, and we saw this already when we so we've seen kernel functions when we talked about SVM, okay? So when we talked about SVM, what we said was we can take a 2D point and project it into 3 dimensions, or we can do something similar with you know, projecting it into higher dimensions and things like that, right? So here's an example. We can take some function phi, and it's going to transform x1, x2 into this vector, x1, x2, and x1 squared plus x2 squared, okay? And we can show that the equivalent kernel function is equal to this, right? So if I transform xa and xb using the phi function, okay, the transform of xa becomes xa1, xa2, and xa1 squared and xa2 squared. And we're going to dot that with xb1, xb2, and xb1 squared plus xb2 squared. Okay. And so if I take the dot product of these, I get xa xa1 xb1 plus xa2 xb2 plus xa1 squared plus xa2 squared times xb1 squared plus xb2 squared, okay? And this part, okay, this is equivalent to the dot product of xa and xb, okay? And then this part, this is the norm of xa squared, and this is the norm of xb squared. So, so this can also be expressed as the norm of xa squared and multiplied by the norm of xb squared. So we can apply a transformation function phi and find the equivalent kernel. This is not the point of kernel functions, okay? This is just to kind of illustrate that they are equivalent, but the point is not to find the relationship between this and this, okay? I'm going to do another example here, okay? And that's going to be it as far as the relationships between phi functions and kernel functions, okay? So here's another transformation function phi, okay? So there's kind of the polynomial kernel takes some constant times plus basically the dot product of xa and xb, and it takes that that quantity and you raise it to the power gamma, okay? And so here, if I use c equal to 0 and gamma equal to 2, then this would be what we call a quadratic kernel, but you can change gamma to 3 or 4 or whatever, and you can also change this c value constant to some other value. But if I use 0 and gamma squared, then the equivalent transformation function would be this. We have x1 squared, x2 squared, and the square root of x1, x2. And we can see that if I apply that to the vectors xa and xb, okay, then I get xa1 squared, xa2 squared multiplied by the square root of xa1, xa2. And I'm going to dot that with xb1 squared, xb2 squared, and square root of 2 xb1, xb2, okay? So we take the first elements, we multiply them together, okay? And then we take the second elements and we multiply them together, and that's equivalent to that. And then we take the third elements and we multiply them together, and you get 2 xa1, xa2, xb1, xb2. And we can see that this is xa1, xb1 plus xa2, xb2 quantity squared, right? So we have this whole thing squared plus this whole thing squared plus 2 this times this. So it's that. So so this ends up just being taking the dot product of xa and xb, okay, xa transpose xb is going to be this, and then taking that quantity and squaring it. Okay, but again, the point of these kernel functions isn't so you find the phi transformation and the equivalent kernel. A lot of times you can just jump straight to the kernel function itself, okay? So, here's the polynomial kernel, and you can read more about these. And, in the case of the Gaussian kernel, or the radial basis function kernel, the equivalent phi transformation exists in infinite dimensions, okay? The transformation is infinite dimensional. I mean, granted, after you get to like the 10th term, they're really, really small and probably don't even matter. But theoretically, it's the equivalent phi transformation function takes your vector and it transforms it into an infinite, a vector of infinite length, okay? But we don't even need that. We don't even need that, okay? We can just use the kernel function. All kernel functions are inner products of vectors after they've been transformed by the function phi. However, we don't even need to think of the transformation itself. So because the kernel function is the result of this times this is an inner product of some arbitrary transformation, a kernel function can also be used as a substitute for an inner product in the original space. Okay, and I'll show you an example. So anytime you see XA transpose XB, you can kind of replace it. Okay, you can say, well, what if I transformed XA using phi and XB using phi? Then the equivalent would be to just apply, replace it with the kernel function. Okay, so so this is where it's going to become useful. Okay, what we're going to do or what we do in k-means clustering is we take points and we assign a point to a cluster based on its Euclidean distance to a centroid. Okay, so what I'm going to do is I'm going to express the Euclidean distance as a vector product, okay, or basically an inner product of vectors here. And so we can say the squared distance of point x to the centroid mu k. So we've got the point x of n to the centroid of cluster k, which is mu k, right? So this is one vector. And then if we wanted to get the squared distance, I can do that vector basically dotted with itself, and that will give me the squared distance, right? So I can do x of n minus mu sub k transpose x of n minus mu sub k, right? And this is going to be the distance from point n to point k. And okay, now how do we express the centroid of cluster k? All right, so the centroid of cluster k is going to be the sum of all the x's that belong to k. All right, so so this is going to be from j equals 1 to n. We're going to take each x sub j and multiply it by the z value. Okay, so the z is 0 if it doesn't belong to the cluster, and z is equal to 1 if it does belong to the cluster. So we're basically we're only going to be adding the x's where the z is equal to 1. Okay, so we're only adding the x's that belong to that cluster. Okay, and then we're going to divide by how many points, and sub k is just the sum of the z's. So we're going to divide by how many points belong to cluster k. Okay, so it's just basically add up the points that belong to cluster k divided by how many points you have in cluster k. And that's going to give you your centroid of cluster k. So I hope that's okay. All right, so don't be intimidated by this slide. It looks a little crazy. But basically, all I'm going to do is I'm just taking this this distance, right? So I think we're okay with saying that the distance is basically this vector dotted with itself, right? So because Euclidean distance is, your x1 coordinates, that difference, square them, plus the x2 coordinates, that difference, you square them, and so on and so forth. And so that's how we're going to get the squared distance here. Okay. All I'm going to do is I'm going to just take the mu sub k and I'm going to just replace it with this. Okay. So I'm going to just plug this thing in for mu sub k. That's all that's going on in the next slide. Okay. So I just say x of n minus mu sub k. Mu sub k is getting replaced with this whole thing. Okay. And this mu sub k is getting replaced with this whole thing. Okay. Whoops. All right. And so just to kind of keep track of all of our subscripts. So this summation here, this mu sub k, this summation will go from m equals 1 to n, and this summation, for whatever reason we've chosen r, will go from r equals 1 to n. Okay, and okay, so let's go ahead and we will apply the transforms, or I'm sorry, the transposes. We'll apply the transpose and carry out the multiplication. Okay. So again, this is still the distance from point n to the centroid of cluster K. So it's fine that xn and xn here are both the same. Okay, so I've got xn transpose xn, okay? And then we'll do, so we have, and then we'll do the inner, okay? So I've got this thing multiplied by this, okay? And, oh, maybe I have the, okay. And then we'll do the next. So we'll take the xn transpose, the outer, okay, the outer xn transpose multiplied by this quantity here, okay, will give me this, xn transpose xr. And then lastly, the last terms, okay, so I'm going to get 1 over n sub k, 1 over n sub k squared, and now I've got a double sum of xm's and xr's, and xm and xr transpose here. Okay, if I look closely, okay, I can replace, all right, I can combine these two together, okay, because 1 over n sub k times, it's actually, if I, okay, if we just focus on the xm times 1 over n sub k sum from zmk to xm, this part is equal to mu sub k, and then this part times this is also mu sub k. So basically, these are both equal to, I should say, xn times mu sub k, okay? So these, both of these things are exactly equal to xn times mu sub k, so I can combine them together. So I get 2 over n sub k, and then we'll leave this as is, okay? So I'm just combining the two middle terms here. It's a bit of a mess. It's a bit of a mess, but what we're doing is we're converting this into kind of just, you know, product. We're just expanding this out here. Okay, so why did I bother? Like, why did I make this all complicated and make my life seem like this? Yeah, I get that. The distance, the squared distance, sure. If you want to leave it in that form, I think that. Why would I do this to myself? Why would I make this, right? Okay, the reason for this, the reason why we might do something like this is because here we've expressed the distance as basically, we've expressed the distance to the centroid without actually needing to calculate the centroid mu sub k itself, okay? So we're expressing the distance from n to the centroid of cluster K without actually using the term of the centroid, okay? The distance is now a product of basically a bunch of x's against each other, okay? And we're just keeping track of, we have to keep track of which x's belong to which clusters, the z's, but we're not actually calculating the centroids themselves. Okay, I'm not sure if you guys can see that. Okay, so we're not actually calculating mu sub k, we're just we've got all of these products of x's here. Okay, so what I can do is I can pretend that I'm going to apply the transformation, okay, apply the transformation phi to every single x here, okay? So I'm going to apply transformation phi onto x, phi onto x, phi onto x, phi onto x, and then, so the inner product of x after applying the transformation is just going to be the kernel. So I've got the kernel function of xn to xn, the kernel function of xn to xm, and the kernel function of xm to xr. So we're going to replace all of these inner products with the kernel functions. And so now this is the kernelized distance to the centroid. All right, you know what? Let me just pause here and give you a moment to give me some feedback, or let me know if this is making zero sense or if it kind of makes sense. Maybe you just want to see an example or something here. I guess I'll give you your first quiz question also. Today is 8th week Wednesday, and our first quiz answer is B. B as in bear or boy. B. Okay. All right, so some of you, 3 people have given me yeses. The rest of you are silent on this, on the matter. All we've done is we've expressed the squared distance between some point x and the centroid as a product of all of these x's. And then now that I've got these inner products, I'm just replacing them with a k to kind of get a kernelized distance. Okay, let me, I think it will be a little bit better if I do an example here. Okay, so again, first quiz answer is B, B as in bear. Okay, so why do we split the mu sub k between m's and r's? So yeah, when you do kind of products of these things, you want to allow for I guess the summations to happen separately and not if you do them, if you have them both with the same subscript, then you're basically looking only at like the diagonal. Like if you have a matrix multiplication or something, like if you have a double sum over a matrix, okay, you're supposed to do every column times every row, and then you would sum the double sum would be you add all the rows together and then you add all the columns together. But if you have it only equal to or xm, where you have the same index, if this was xm and this was xm, then you'd effectively just be going down the diagonal of the matrix. So this is basically when you have a double sum, you're basically taking 2 matrices, and you are or you're basically taking 2 vectors, and then you're kind of multiplying them, and you're getting like a resulting matrix, and you're adding up all the elements of the matrix. If you only if you have the same index on these, you're basically just adding up the diagonal. So that's why we have separate m's and r's here. I hope that makes sense. Okay. All right. So so this is what we have. Okay. So let me show you how this works. Okay. So when you do kernelized k-means clustering, you're going to start off and you're going to determine how many clusters you're going to search for. That's the same. Randomly assign your points to each of the clusters. That part remains the same. Okay. And then now we don't even bother calculating the centroid. We're not going to calculate the centroid. We're going to just straight reassign based on the current assignments. We're going to calculate the distance to the centroid without even calculating the centroid to it. Centroid, okay? So without even calculating what mu sub k is, we're able to calculate the distances, okay? Just using the assignments. We've got the x values and the assignments in z, okay? So just using the assignments and the x values, we can calculate the distance to the centroids and then reassign them directly, okay? So we're going to repeat this step of reassigning values to clusters by associating the values in the data set to the nearest centroid using that kernelized distance. And we don't even have to calculate the centroid itself, okay? So we no longer need to find the actual centroids. The kernelized distance will find the distances to the centroids directly, right? So we're going to try this with a very simple data set. We're going to do kernelized k-means clustering twice, okay? So first, I'm going to just show you how it kind of what it's doing is I'm going to do it the old-fashioned way. I'm going to take the 2D data. I'm going to use a kernel function that is equivalent to transforming it into 3 dimensions. So I'm going to take 2-dimensional data. I'm going to transform it into 3D, and then we'll calculate Euclidean distance in 3 dimensions. Okay, which would be basically, you know, we're going to be using this. We're calculating the centroids itself. We're going to find the Euclidean distance to the centroid like that way. Okay, so I'm going to do that first. Okay, then I'm going to do it again using this crazy messy formula. Okay, and we're going to see we get the same distances and the same results without having to actually do the data transformations. Okay, so here is our data. I got 8 points. 4 are going to be very close to the origin, and 4 are far from the origin. Okay, so I got 8 points, 4 right here, and 4 that are far away. And so if I use regular k-means clustering, which uses Euclidean distance in 2D space, we would see that, like, it's not going to cluster, right? Because it's going to say this data point and this data point are as far different as they can possibly be according to Euclidean distance, right? And this corner and this corner. So if we're using Euclidean distance in 2-dimensional space, this data point and this data point will never be in the same cluster because they are as far apart as we can possibly be, right? But you know, if I said group the similar observations together, there might be something in your in your heart that says, like, these ones seem really similar and these ones also seem similar. Okay, and you might want to put this data point in the same cluster as this data point. Okay, but if you're doing that, you're not using Euclidean distance, okay, as the measure of similarity. You're using something else, right? And what you're probably doing in our head is we're applying some kind of transformation. Maybe we can't articulate it as such, but we're applying, we're saying, we're looking at some other aspect, right? Where maybe we're saying, you know what, they are similar in terms of their distance from the origin, right? These are very similar because they're very close to the origin, and these 4 are similar because they're like equidistant from the origin. They're far from each other, but they're far from the origin, and that makes them similar or something, right? There's something here that kind of compels us that says this. But regular old k-means clustering will never put this one and this one together because as far as it uses Euclidean distance as a measure of similarity, and these are very far apart, so they're never going to be in the same cluster. Okay, so what I do is I'm going to apply the transform. So we got, when we apply the transform, it goes from x1, x2 to x1, x2, x1 squared plus x2 squared, okay? And so x1 squared plus x2 squared, x1 squared is 0.01, x2 squared is 0.01, and when I add those together, I get 0.02. 2 squared is 4, and 2 squared is 4, and when I add those together, I get 8, okay? And I do start off with random assignments, and we end up with these 2 points in cluster 1. I'm sorry, and this point. So we got 3 points in cluster 1 and 5 points, these points, and these points in cluster 2. All right, and so I think I actually have a visual here. How do I do this? Okay, all right, so let me, does that work? How do I? Get my little window to pop up. Oh, this is the one I need. Okay, so, sorry. This is the thing I wanted. Okay, so I don't know if, can you guys see my screen here? And all right, so we have, so we've got, I hope you guys are able to see, I've got 5 points, this point, this point, and this point, and this point and this point in red, and I've got 3 points in the blue cluster 1, which is this point, and this point. Okay, so this is what it looks like after I've transformed it into three-dimensional space. All right, and so that's what this is trying to show here. And what we'll do is, so now that I've transformed them into three-dimensional space, okay, I'm going to calculate the centroid of each of these clusters. So I'm going to take this point, and this point, and I'm going to add them together. So I get -2, -2.1, plus 1. So that adds up to -2. This also adds up to -2, and this adds up to 8.02 and 0.04. So 8.04 divided by, and I'm going to divide by 3. Okay, so -2 divided by 3 is -0.667. 2 divided by 3 is 0.667. And then, what did I say, 8.04? 8.04 divided by 3 should be 2.68. Yeah, 2.68, okay? And I do the same thing with the other cluster. I've got 5 data points in there, those things, and when I add them up, I'm gonna get, the centroid is 4.808, okay? And so when it's hard to see in this thing, so let me see if I can plot it. So I run that, and I run that, and okay, so this represents the centroid of, so I've got the centroid of the red points, and I've got the centroid of the blue points, okay? Oh, geez, I don't know how to. All right, so here is, so this is the centroid of the red points up here, and the centroid of the blue points down here. Okay, which makes sense because, you know, as far as the blue points go, there's 1 up here and 2 that are down here, so the blue point is going to be lower. And then as far as the red points go, there's 2 points on the bottom and 3 points on the top, so the centroid is going to be closer to the top there, right? And then you know, you've got nothing over on this side, so it's getting pulled in this direction. So anyway, this is that's what the centroid looks like in 3D space. Okay, and so what I will do, okay, so that's that. So we've got the, so these are supposed to be the centroids represented in 3D space. It's hard to see in a two-dimensional plot. And this is the plot RGL is the, so you can, so if you want to create your own little 3D things, this is the library you use, plot 3D RGL, and you can use, you know, do points 3D and plot RGL here. Okay, so anyway, I'm going to calculate the distance to centroid A, and so it's just basically this minus this squared plus this minus this squared plus this minus this squared, so I don't think any surprises here. And then we calculate the distance from each point to centroid B, and so we do this minus this squared plus this minus this squared and this minus this quantity squared, and the distance to centroid B is farther, and so we're going to say, okay, between these two, which distance is closer, we're going to assign to centroid A. So we calculate the distance from each point to centroid 1 and centroid 2, or centroid A and centroid B. And then we compare those distances and we say, all right, which one is closer? And so we do that. And so all of these, the distance to centroid A is closer. So they get reassigned to cluster 1. And then we do the distances here. And all of these, the distances to centroid B are smaller than their distances to centroid A, so they all get assigned to cluster 2. Okay. And so when you do this, the resulting plot looks like this. that, and let's try this. Okay, so now this seems a little silly. Okay, so we can see the centroid of this cluster is right here, you know, on top of the cube, and then the centroid of the bottom cluster is at the bottom of the cube there. Okay. All right, and then if we say, all right, now measure the distances again. Okay. All right, so we can say, all right, what is your distance? So this is the centroid of cluster A, 0.02. Centroid of cluster B is 0.08. Okay, and we can say, okay, what is your distance to the centroid of cluster A? All right, they, you know, this squared plus this squared is 0.02. And, you know, what's your distance to this centroid? It's quite far, okay? And then, and what's your distance to each of the centroids? And it's pretty, these points are pretty far away from this centroid, but they're a lot closer to the centroid up there. So if we reassign points, we would say end up with the same assignments. These 4 end up in the first centroid. These 4 end up in the second cluster. And because none of the assignments have changed from here to here, we would say it has converged. Oh man, it's already 10:40. Okay, so so that was how it works when we transform it and then we calculate the distances, right? Okay. So so here we are going to do this. We're going to have to calculate a K matrix, okay, for every possible combination of one of each of our X values and each of the other X values here, okay? So I've got 8 data points, so I'm going to have to create basically an 8x8 K matrix, a kernel matrix of basically every X value crossed, you know, found with every other X value, right? Because here I want basically the double sum of all of the X combinations here. Okay, so again, our original data is in 2 dimensions, and these were the original random cluster assignments that I started off with. I started off with these random cluster assignments. And so using that, we are going to calculate these kernelized distances without bothering to calculate the centroids, okay? So if I, so here I'm just filling out the kernel matrix, okay? Which is gonna basically be the product of, so I'm taking this kernelized distance and I'm gonna find this for every single possible combination. I've got 8 values in X and I have to kind of cross them with every other value here. And so I just get this big matrix. And then we're gonna calculate the double sum. All right, so basically I'm gonna just take every single value in here and we're gonna multiply it, you know, for R in 1 through N and M in 1 through N. I'm gonna take, multiply Z times Z times the kernel. So basically I'm just applying this thing, and then the total product is, or the total double sum is 72.646, okay? If you're familiar, if you're okay with some matrix operations, you can actually do a cross product between Z and itself. But anyway, don't worry about this, but you can also find it this way. Okay, so I'm going to go ahead and I'm going to find these kernelized distances, okay? And so these are the distances of each value to the centroid of cluster A, based on the assignments of dots that belong to cluster A using basically that vector Z. So the vector Z is who belongs to cluster A. The assignments are 1. So it's basically just knowing that this point, and this point belong to cluster A. I have calculated these distances to A. So look at these values: 7.984, 8.251, 7.717. If I flip back to this this slide, okay, where I calculated the centroids in three-dimensional space, and I calculated, I calculated these centroids by doing the transformation and doing that, and I got the distances to the centroids. I get the same value: 7.984, 8.251, 7.717, and 7.984. Same distances right here. Okay, and I can do the same thing for distances to B: 23.26, 23.104, 23.424. Flip back to that slide: 23.26, 23.104, 23.424, so on and so forth. Okay, so I know this formula is absolutely crazy looking, okay, and it's a nightmare, and it's actually, it's kind of difficult, not difficult, but you have to do all of this kernel matrix stuff and take all of these sum products and all of that. This is kind of a nightmare to deal with, but the advantage is we can use this we can get these kernelized distances. So this is the key. We can get the distances to the centroids without actually finding the centroids themselves, right? So like, I think back here, like it makes sense for our brains. Like we plot it, and then we say, all right, it's in 3 dimensions. I can find the centroids right here. Okay, like this makes sense to our brains, I think. Okay, and we can say, all right, if this is the centroid and this is the centroid, I can get the distances between. I mean, if this is the centroid and this is the data point, I can get the distance between here and here. That's fine, and I can get the distance from here to here. But it required us to find these centroids. So the crazy thing about this formula is you can get these same numbers, these same distances, without actually calculating the centroids themselves, okay? Just by applying this kernelized function and this double summation thing. I think that's impressive, okay? And this is gonna be very important for us because we need to, at some point, we might want to use like that Gaussian kernel, which transforms things into infinite dimensions, okay? And if something exists in infinite dimensions, we're not going to be able to calculate the centroid, and we're not going to be able to calculate the distance to that infinite dimensional centroid, at least not practically, okay? Okay, so anyway, here are the resulting distances. And again, if you take a look at these numbers and you compare them to the values on slide 35, it's the exact same numbers, okay? And then so we say, all right, which ones are closer? And then we're going to say, all right, all of these get assigned to these first 4 points get assigned to cluster 1. The last 4 points get assigned to cluster 2, based on saying which one has the smaller distance. Okay, and then whoops. Okay, sorry, I needed to break this onto another slide. Okay, but anyway, so this should go on to another slide, but if you do that, you get the same resulting distances, okay? Something's a little off there. Okay, and so we can, yeah, okay, and so we get the same distances that we found earlier on, I don't know whichever slide it was. Okay, so this is just a mess of code. All right, and so let me just kind of show you, like, if you do this, all right, so here I'm just going to create this crazy plot here, okay? And we want to cluster these, all right? So again, if you use regular k-means clustering that uses Euclidean distance, it will never put this data point up here and into the same cluster as this data point down here, because Euclidean distance says these 2 points, this one down here and this one up here, are very different from each other. Their distance is far, and we only cluster points that are similar, meaning they have small distances together. So we got to apply some kind of transformation here, right? And so, so if I did k-means clustering, this is the result, and it ends up putting these ones together and these ones up here, and it doesn't put any of these points up here together with these ones, okay? So that's just the result of running k-means clustering. And you could imagine if I ran it multiple times, we would get probably some variance of this, but probably rotate it around, because just arbitrarily it's going to end up different. Okay. So again, it's using Euclidean distance, so it's not going to work. All right. What we can do is we can apply a Gaussian kernel. All right. So I'm going to apply a Gaussian kernel, which is this, and I'm arbitrarily choosing gamma equal to 1, but you could choose different gammas, and you kind of messed around with what like different values of gamma will do. And this is what kernelized clustering will look like. So I'm just going through and I'm running some values here. And so after one iteration, it does this, which like my brain can't comprehend what it's doing, because what it's doing is it's transforming it into infinite dimensional space, and it's saying in infinite dimensional space, this is how it should get reclustered. Okay, and again, and it's still reclustering in this higher dimensional space, and so somehow iteratively it goes like this, and it ends up like this. Okay, which to us I think makes intuitive sense. It groups the ones in the center closer together, and the ones out here together as well. But again, exactly how it's doing that is a mystery to us, because it's existing in infinite dimensional space. Okay. Okay. So how does this work? All right. I don't know. I just did a similar example, silly example, right? So let's say, let's say I said you have to cluster people or actors together. Okay. And in some cases, like, it doesn't make sense to have a centroid, okay? A centroid, like, a person is a complicated thing that maybe can be described in some kind of infinite dimensional space, okay? And, or not infinite, but high dimensional thing. And there's all sorts of things you can talk about. And so, what is a centroid? What is this quote unquote average human, average person? Is a weird thing, right? And so I just said, I don't know if you're familiar with these actors, but what if you took Chris Evans, he plays Captain America, Chris Hemsworth, who plays Thor, and Jason Momoa, who plays Aquaman or Khal Drogo or whatever, in one cluster. And then in another cluster, we have actors like Joseph Gordon-Levitt and Jesse Eisenberg and Adam Scott. I don't like, I don't know if you, Joseph Gordon-Levitt. Okay, so I don't know if you're familiar with these guys, right? So that's one, and here's Jesse Eisenberg. So he was in The Social Network, and Adam Scott is in Parks and Rec. Okay, and then compare these to Hemsworth, and I don't know. Okay, so anyway. I like all of these actors, but then, we would say they're definitely like different, right? They play different roles. Like it's hard to imagine Joseph Gordon-Levitt in the role of Thor or something like that, right? Like something, or, it would be hard to imagine Jason Momoa playing Mark Zuckerberg in The Social Network, right? That like something doesn't quite line up there, okay? And so, but if I say, what's the centroid? Like, we can cluster these actors together, but I say, what's the centroid? There's no centroid. Like, you can't have like a person that exists as the average of these things. But can we take new actors and try to cluster them and say, like, are you more similar to these characters or these actors? Or are you more similar to these actors, right? And so you get something, and you would kind of compare, whoever your new actor is, or new observation to the values that exist. And so you're basically using, without actually calculating the centroid itself, okay? You're taking kind of some distance metric between each observation, okay? And kind of the currently existing ones. Okay. That's it for today. Oh, second quiz question is, E for elephant. E for elephant is your second quiz question. Anyway, I think it's kind of neat that you can apply these kernel functions, which we've already seen from support vector machines. And you can apply it to find these distances to centroids, even though you can't actually calculate the centroid itself. So, all right, that's all. E for elephant for the second quiz question, and we'll call it a day there, and we'll see you guys on Friday.